All right, guys. So one thing that we want to do is we want to use the concept of equivalent circuits like we did when we started taking a look at resistors in series and in parallel in order to define now what it means for inductors to be in series and how we can find an equivalent inductor given a network. So let's go ahead and begin some mathematical derivations. So this is inductors in series. And I'm going to begin with essentially two circuits. The first circuit contains a set of three inductors. And each one of these inductors is characterized by an inductance L1, L2, and L3 initially. And what we want to do is we want to be able to take this network and replace it with a network of a single inductor that contains an equivalent inductance like this. Now, I can definitely say also that there is a total voltage across the entire network, and there's going to be a certain amount of current, I, that's going to go in through that terminal. Now, if these are going to be truly equivalent circuits, then the voltage across the equivalent inductor and the current flowing in through its node must be absolutely the same. And again, this is if they're going to be equivalent circuits. Now that I have those inductors on the circuit on the left defined, notice that I can identify some nodes here. There's a total of 4 nodes there. And I can also define voltages and currents for each one of those inductors. So across the inductor L1, there's a voltage V1 and there's a corresponding current I1 flowing through it. For the second inductor L2, there's going to be V2 across it and I2 flowing through it. And lastly, for the third inductor, you guessed it, there's V3 volts across it and I3 flowing through it. And remember that the total voltage across the entire network of inductors is V. Now, one of the things that we can definitely say, and this is something that's going to simplify our analysis quite greatly, is at each one of these nodes, I can actually apply KCL. And if I apply KCL at each one of those nodes, remember, whatever current's flowing in is the same current that needs to flow out. So one of the things that you, hopefully by using KCL by now, you should be able to see immediately is by KCL at the nodes, we should have that I1 is the same as I2 is the same as I3, and it's the same current flowing into the entire network, I. Now this is an important relationship because this is what defines elements in series. This is literally the definition of elements in series. When by KCL we're forced to conclude that all of the currents are the same, that's what it is meant. So this defines our inductors in series. And we'll see how this gets used here in a second. Now, to keep on going with the analysis, one of the things that I need to remind you guys of are the IV characteristics for inductors. So for inductors, hopefully you should be able to recall that the voltage across the inductor is equal to the inductance L times the time rate of change of the current. And we're actually going to apply this a total of 4 times. So here we're going to apply this 4 times. The first time is across the inductor L1, then across the inductor L2, then across the inductor L3, and then across the equivalent inductor in the other circuit. So immediately by applying this formula, I can write down that V1 is equal to L1 times the I1 dt. V2 is equal to L2 di 2 dt. V3 is equal to L3 di 3 dt. And on the circuit On the right-hand side, we also have that V is equal to L equivalent di dt like this. Right? Now, this is as far as we'd be able to go in our analysis unless we actually used KVL as well, right? And one of the things that we can do is if we actually apply KVL in moving from there to there, from that node, the left node to the right node, we should be able to see that the total voltage V is just the linear sum of V1 plus V2 plus V3. So by KVL, we should have that V is equal to V1 plus V2 plus V3. Now I can actually use these relationships in here, right? Direct substitution. So I have V is equal to L1 di1 dt plus L2 times di2 dt plus L3 times di3 dt. And this is where our defining property comes in useful. Those three currents must be the same. So I can replace di1 dt, di2 dt, di3 dt just by di dt. So I have V is equal to L di dt, L2 di dt, L3 di dt. And all three of these terms are identical, right? So we can factor them out. So we have V is equal to L1 plus L2 plus L3 di dt like this. And this is where the beauty actually comes in. So I'm going to call this equation 1. I'm going to call this one equation 2. By equivalent circuits, if the circuits are going to be equivalent, then this voltage, that voltage must be the same. Otherwise, they are not equivalent circuits. So I can equate, by equivalent circuits, I can equate equations 1 and 2. So by equivalent circuits, we have 1 is equal to 2, in which case I have L1 plus L2 plus L3 di dt on the left-hand side. That's equal to L equivalent di dt on the right-hand side. And as long as di dt is not 0, those two cancel out. And the relationship that we're left with, I'm going to rearrange it slightly, is that L equivalent is equal to L1 plus L2 plus L3. This is what we wanted to arrive at. This is how we add inductors in series. So if I happen to have a network of inductors in series, and by KCL, all of the currents in each one of the inductors is forced to be the same, I can replace them with a single inductor as long as the equivalent inductance is the sum of the individual inductances. And that's what we wanted to get to.